Hello, everyone. So this is Alex here. I'm presenting question 1 of quiz 2 today so question 1 of quiz 2, it's a projection matrix question, and it says that if xx pseudo inverse, I'll call it xx plus, it's p, then and it has x is rank R. Okay, so there's R of them that R columns that are linearly independent, and then xx pseudo inverse can be written as, or xx plus can be written as the sum of I rows of, let me switch over to the notepad. So sum of I ui times ui transpose, like that. Okay, so how do we do this question? It's not too hard. You just need to use the singular value decomposition. Okay, so which states that x is u times sigma times v transpose, where u and v are orthogonal matrices. And now if x is n by p, then u is n by n, sigma is n by p, and v is p by p. Okay, so u and v has to be square matrices because they are orthogonal. Okay, like orthogonal matrices by definition must be square matrix. So if it's orthogonal, notice this property: u transpose u must be in, v transpose v must be ip. Okay, so x times x pseudo inverse is x is u sigma v transpose times u sigma v transpose pseudo inverse, and this part on the right, u sigma v transpose pseudo inverse, you can think of that as just breaking down this pseudo inverse into two components. So you have u times sigma pseudo inverse over here times v transpose pseudo inverse, and then doing that again, you get sigma pseudo inverse u pseudo inverse. Okay, and so now we just need to evaluate this part and this part separately using the property of orthogonal matrix. So if u is full rank n, okay, then u pseudo inverse is u inverse. All right, if it's full rank n and it's square matrix, then there's no point of using pseudo inverse, because pseudo inverse is for rectangular matrices. Okay, there's a strict inverse for square matrix if this is full rank and it has that. So u pseudo inverse is just u inverse, and similarly v transpose pseudo inverse is just v transpose inverse. Now, any orthogonal matrix, the inverse of that is the same as the transpose. So this means that this turns into v transpose transpose, which is v, and u pseudo inverse is just u transpose. So the whole thing just becomes xx pseudo inverse equals to u sigma v transpose times v sigma pseudo inverse u transpose. And notice you have v transpose times v over here in the middle, and whenever you see that, that just becomes identity. Okay, because they're orthogonal matrix. Oops. Okay, and then writing up everything else, you get u times sigma times ip times sigma plus times u transpose. And so what do we know about sigma? Okay, actually write one more line, so get rid of the I. Right, one more line. So you have sigma. Now sigma is a row. It's a series of you can think of this as like a diagonal matrix with square roots of eigenvalues ordered from largest to smallest. Now the thing is, because this is rank R, that automatically means sigma is also rank R, which means this matrix, in fact, actually only has R diagonal elements, and everything else is 0. And then, if n is greater than p, there will be n minus p rows of zeros. So this is actually what sigma looks like. Okay, it's always nice to look back at the first principle, so we actually know what the heck is going on. Now, the pseudo inverse of a diagonal matrix, actually, it's you can think of that as just 1 over the diagonal entries. Because if you think about it, the point of pseudo inverse is to make basically like to cancel out your zeros, cancel out your diagonals so that you get like identity, right? Like it's an inverse. So an inverse, just basically an inverse of a diagonal matrix, you just get a whole bunch of ones essentially. So same thing here. Okay, so you just get a bunch of zeros. There's n minus p columns, and then a whole bunch of zeros here. Okay, a whole bunch of zeros. So when you multiply these two things together, you'll actually get an R by R identity matrix and 0 everywhere else. So when you have these 4 things multiplied together, and considering that U is an orthogonal matrix, then you just have a bunch of U1s to UNs multiplied by identity 0, 0, 0, multiplied by U1 transpose all the way to UN transpose. And then you just pretty much get the sum of a bunch of orthogonal matrix, because this is obviously if you write it in vector form, then you can write it as a sum. Okay, so you just end up with this. Oops, let me rewrite that. So because there are only R1s, okay, R1s, then you only take the first R of these vectors. So first R of these vectors, and then UI transpose. And there we have it. That's our answer to question 1. Thanks, guys, for listening. Good luck with your studies.